So folks, we've worked with the difference quotient now several times in this class, and what we've done each time is we've sort of kept the idea of the difference quotient exactly the same, but we've applied it to more and more complicated functions. And so this time we want to look at applying the difference quotient for rational functions. So in class we'll review a little bit about what we mean by the difference quotient one more time, that idea of average rate of change, or the instantaneous average rate of change, or the slope of the secant line. But in the meantime, let's just recall the mathematical definition of the difference quotient. So this is the difference quotient. And remember that it's defined to be, well, it's the average rate of change, or it's the slope of the secant line connecting x to x plus h, but we give it as f of x plus h minus f of x all over h. That's our difference quotient. I want to remind you that something has happened here. The difference quotient would have originally been set up as the slope of the secant line, meaning it was originally set up this way, but of course the two x's in the denominator add out, leaving us with just the factor, or the term h, in the denominator. So I'm pointing that out because I think that if you look at it this way, it's a little bit easier to see the difference quotient is really just the slope of a line connecting 2 points on a function. But once we add out the factors of x, that becomes a little bit harder. Okay, so that's a review. We'll get more of a review in class. In the meantime, I'd like you to practice doing the difference quotient on this radical expression, which is not what we're learning today. We've already tested on this. I'll help you get started, and then I'll turn you loose to using the included solution. So the difference quotient for this radical expression would be g of x plus h minus g of x all over h, and that's our average rate of change. And we would compute that by doing the square root of 1 minus 2 times the quantity x plus h minus the square root of 1 minus 2x all over h, where here we replace the x in our expression here with the expression x plus h, whereas over here we replace the x with just, of course, itself, x. Okay, and now you'll finish. So you finish, and you have a hyperlinked solution for you. So pause the video and finish that out. Okay, folks, so now that you've done that, let's go ahead and find and apply the difference quotient for our first rational function. Notice that it's called a rational function because we can think of it as one polynomial divided by another polynomial. One isn't the most exciting polynomial. If you look at the next page there, that looks a little bit more like a rational function. But let's go ahead and apply that to this function right here. So we would say that our average rate of change, which is the same thing as the slope of the secant line connecting x to x plus h, but that's equal to f of x plus h minus f of x all divided by h. So in our case, we would have 1 over x plus h minus 1 over x all divided by h. Clean that up slightly. So here we can see that we took and we applied the difference quotient to this new function here, and hopefully that's beginning to feel a little bit routine. We've done it for polynomials, we've done it for radicals, and now we're doing it for rational expressions. So what is hard then is, where do we go from here? So this is the difference quotient, and I guess technically I found it, but always it's implicit that we want to simplify it as well. So what we're going to do is, notice that this built a complex fraction. Remember the idea of a complex fraction that we've been studying? We've got fractions nested inside of fractions. So what can we do? The trick for dealing with complex fractions generally is to clear out the complex fractions by multiplying both the numerator and the denominator by the LCD of those minor denominators. Remember that this is just the convenient one trick that we've seen before. So then what I can do is I can distribute that LCD in the numerator, and of course distribute in the denominator, although that's not very hard. In the denominator of this fraction, we would have h times x plus h. And in the numerator, when we distribute it through, notice that we would get, for the first distribution, the factors of x plus h and x plus h, these two factors would cancel or divide out, and so I'm just left with 1 times x minus, and then when I distribute here, the factors of x cancel, so I'm left with this 1 in the numerator times this factor of x plus h yet. And now we just go ahead and continue to clean this up. I guess I've used up a lot of my room. I should have been more careful. So this would give me x minus h in my numerator. Be very careful there, folks. Notice that I distributed that minus sign to both expressions, and that happens a lot in these problems. By virtue of it being a difference quotient, you will often have to watch out for distributing negative signs. In the denominator, we still have the factors h and x times x plus h. Simplifying, notice the factors of x, or the terms of x, add out, and so I'm left with negative h divided by h times x plus h. But now I can divide out those factors of h, and I'm just left with negative 1 in the numerator after I divide out an h, divided by x times x plus h. And there it is. I've simplified that difference quotient about as far as I can, and we'll leave it there. Okay, folks. So let's go ahead and do this one more time, but with a slightly more complicated function. So again, we want to find the average rate of change, and we'll learn why that's important when we get to calculus, which is the same thing as saying let's find the slope of the secant line connecting x and x plus h. We'll review that idea in class. But what is the difference quotient here? It's g of x plus h minus g of x all over h. And so what we're going to do is we're going to take our function g, and we're going to apply the difference quotient to it. So here, everywhere I see the expression x, I'm going to replace it with x plus h. So that gives me 5 divided by 3 minus 2 times x plus h minus 5 over 3 minus 2x, all divided by h. And then remember, so we've now applied the difference quotient to g of x in these two expressions here, that when we do this with a rational expression, we usually end up with complex fractions. So I'm going to take this expression, I'm just copying it here. I'm going to go ahead and distribute this 2 through. You don't have to do that. That's sort of dealer's choice, and I'm not going to lie, I don't always do it the same way every time. And I'm just copying that original expression with the exception of having distributed that minus 2 through. And then remember that this is a complex fraction, and so let's clear out the fractions by multiplying by the LCD of the minor fraction. So here's one denominator, here's another denominator. So we're going to multiply this by 3 minus 2x minus 2h times 3 minus 2x all over itself. That's that convenient one trick that, boy, it shows up everywhere in math. So then we'll distribute that LCD to both terms in the numerator and as well as the denominator. In the numerator, notice that these two factors, the 3 minus 2x minus 2h, in both the denominator and in my LCD, those two factors cancel or divide out. So I'm left with just 5 times 3 minus 2x minus, and then here when I distribute to the second term, it's the second factor in the LCD that divides out. So I'm left with 5 times 3 minus 2x minus 2h, all divided by h times 3 minus 2x minus 2h times 3 minus 2x. And now we'll go ahead and distribute our 5s through and do some 5 or negative 5 and do some cleaning up. So I end up with 15 minus 10x minus 15 plus 10x plus 10h. Be very careful as you distribute that minus 5 to this minus 2h. That becomes a positive 10h divided by the denominator, which we'll just recopy. It gets a little tedious having to recopy these denominators, but one of the things you're learning how to do in this class is how to manage large expressions. And then let's look at what cleans up here, folks. And I apologize, I'm going to have to make my work here a little bit smaller. I apologize for doing that to you. There's just no way I can get it all in. Should have given you a little more room myself. And so then as we clean this up, the factors of 15 add out, the factors of 10x add out, and so I'm just left with 10h, all divided by h times that denominator. And now the factors of h divide out, and so I'm just left with the numerator of 10 divided by 3 minus 2x minus 2h times 3 minus 2x. And there it is. We've cleaned it up. Okay. So folks, hopefully we see, and if you're finding this difficult, these are challenging problems. These problems are difficult for even my Calc 1 students as they do them. Okay, these are tough problems. But hopefully you see that the idea of the difference quotient still hasn't changed. It's still that ratio. And we still tailor the difference quotient for our specific function. So we replace all of the x's in the first expression with x plus h, like we did right here, copying it over as the second expression. And then every single time you do the difference quotient, you get to here, and you have some trick that you have to perform to try to clean it up. The trick that we're performing in this time is to clear out the minor fractions by multiplying by the LCD of the minor fractions over itself. Okay, folks, that brings us to the end of this pre-work video. And that actually is enough for you to finish this out. You'll notice that I've got one more for you to try that has a solution, and then a challenging one for you to try that does not have a solution. Notice it doesn't have a solution here, but you'll want to just mimic the work of number 5 above here. So it'll be the same work, just with different numbers here. So give that a shot, and I will see you in class. Bye-bye.